Good day, everyone. So welcome to the week number 8 of our Fundamentals of Electric Circuits 2. Okay, so for this week, our module or our topic is about sinusoidal steady-state analysis. Okay, so let's before we proceed, let's recap first our topics that we have discussed so far in our course. So we started with a review of capacitors and inductors and their behaviors on AC, AC, and their behaviors on AC. Okay, and then we had RC circuits, RL circuits, first order, and their natural and step responses. And then we have, for our latest discussion, we had the second order RLC circuits and also their natural and step response. Okay, so this time we will go to our source, the sinusoidal steady state analysis. So this refers to our source, voltage source and current source. Okay, AC, of course. So for the learning outcomes of this module, we have 3. First, learn how to analyze circuits powered by time-varying voltage sources. Number 2, know how to analyze circuits powered by time-varying current sources. And then number 3, understand what phasors are and how to transform them. Okay, let's proceed. So define first what are sinusoidal sources. So a sinusoidal voltage source produces a voltage that varies sinusoidally with time. Similarly, a sinusoidal current source produces a current that varies sinusoidally with time. To express a sinusoidally varying function, we can use either the sine or the cosine function. Though either works really well or equally well, we cannot use both simultaneously. Throughout the discussion, we will use the cosine function. Hence, we write sinusoidally varying voltage as, so this will be the working equation of our sinusoidal varying voltage. So we have V, instantaneous voltage, is equal to Vm, maximum voltage cosine of omega t plus phi. Okay, so we will discuss each of this component in our working equation for a sinusoidal source. Okay, so this is a sinusoidal voltage. From the word sine, okay, so this is a sine or cosine function. So either will do. What is the difference between sine and cosine function, by the way? Right, so cosine, this one, sine, this one. Or I think I'm wrong. It's hard to draw. Goodness. I think there was, yep, I'm wrong. So whatever, let's just search. Okay, so this one, the sine and cosine. Yep, they're not really the same because as we, if you can recall, For example, 90 degrees, cosine 90 is 0, sine 90 is 1. Cosine 0 is 1, sine 0 is 0. So this is the difference. I've been drawing it right, but I don't know. Drawing is not for me. So anyway, let's go back to our figure here. So this is a cosine function. I mean, the discussion will be using cosine function because as it stated, it cannot use sine and cosine at the same time for some reason, which will be explained later. Okay, so this is the parts of our equation. Again, V is the instantaneous voltage, the blue line. Okay, so the value of V depends on time. Okay, so there will be times that the value of V is very high, times that the value of V is 0, times that the value of V is negative, depending on what time instance are we talking about. Okay, next we have max voltage or VM. VM is the maximum amount our sinusoidal voltage can have. Okay, so it can or rather the sinusoidal voltage will alternate from the positive maximum voltage to the minimum maximum voltage and vice versa periodically. When we say periodically, and in a constant pattern or in constant time pattern. Okay. Then cosine omega will be discussed later. So time and then phi will be discussed later. So here we are only discussing about V and Vm. So again, V is the value of the voltage which varies over time. Vm is the maximum voltage the sinusoidal voltage can acquire or can have. Okay. Next, we have frequency. I'm sure you heard about frequency a lot. If you still are confused what frequency is, okay, for example, you are tasked to write letter A on a blackboard and you are given 10 seconds to write as many letter A as you can. If you have written 20 letter A's for 10 seconds, that means you can write 2 letter A's per second, right? So 20 letter A for 10 seconds. So meaning you can write 2 letter A's per second. So this is your frequency. How many can you do in a certain period of time? So this is your frequency in writing letter A in the board. In the case of our sine function, okay, so the frequency is how many times a sine function will be completed in a certain period of time. Okay? So our sine function is complete when it repeats the pattern. For example, this one. This is actually one complete cycle because the pattern is this one and this one. Okay? Wait. I think I'm wrong here. So in the case of our drawing, so in this example, the graph is going upward here, and it will go upward here at this point again. So the pattern will be repeated. So this is one period. Okay? Period is T. Okay? T is period. Period is the time it takes to complete one cycle or one revolution of our sine wave. Frequency is how many revolutions can our sine wave make in a certain period of time. Like for our example on the letter A's earlier. Usually, frequency is expressed in per second or hertz. Hertz is equals to per second. So the formula, the unit we use for frequency is hertz. And hertz, the equivalent of hertz is 1/second or per second. Okay, again, T is the period of how long it takes for one cycle to be completed. Frequency is how many cycles can our sine wave make per second. We usually hear frequency in terms of our, let's say, gadgets. We have our PC, for example, 2 megahertz CPU. Okay, mega is 2 times 10 raised to 6. So 2 times 10 raised to 6 hertz. That's 2 megahertz. So that's how many cycles a CPU can complete in 1 second. So that is 2 million cycles. Right, 2 times 10 raised to 6. Yeah, 2 million cycles. So if you have 2 million numbers to add, the computer can complete it in 1 second. So that's what 2 megahertz per second means. Right. Other instances for our radios, for example, we have kilohertz for AM radio, megahertz for FM radio. For our television, we have megahertz and we have gigahertz. For that, giga is times 10 raised to 9 frequency. And others, our voice, speaking voice is also a sine wave function. The range of our voice is 20 hertz to 2000 hertz. Okay, so that's the range of our frequency, or voice range frequency. What else? What else can I give us an example? Our power source, which is what actually we're trying to deal with in here. Our household power source here in the Philippines is 220 volts, 60 hertz. Okay, so the frequency of our power source in here is 60 hertz, meaning it can complete 60 cycles in 1 second. Okay, so that's what frequency means. Frequency and period. So if you have questions, again, please write it in the chat box and we will try to answer. So that's it for our frequency and period. Okay, let's proceed. So next, we have our omega. Omega is equal to 2 pi f or 2 pi over t. Okay, so 2 pi times frequency. What does 2 pi means? I hope you're still familiar with 2 pi. Okay, in the case of our circle, if we will make one complete revolution around our circle, if in degrees, that is 360, right? If we convert it to radians, that is equal to 2 pi rad or 2 pi radians. Okay? So omega is 2 pi times frequency, meaning how many complete revolutions? Omega. Okay? How many complete revolutions our sine wave can do in a certain amount of time. So times the frequency. So that's why it is 2 pi f or 2 pi over t. So that's omega. That's from our formula omega t plus phi. Okay. So next is the phi. By the way, this is the conversion from degrees to radians. So 180 over pi, because 360 is equals to 2 pi. Okay. Going back to the formula, okay. Or let's discuss phi first. Yep. Going back to the formula. So this is phi, by the way. Phi is what we call the phase angle. Okay, phase angle. If you're wondering what is phi, so that is the that's a Greek letter. Okay. So that is phi, but you usually hear it as phi somewhere, I'm sure. Anyway, so the conversion from degrees to radians is 180 over pi. Why is this mentioned? Because let's go back to the formula of our voltage, instantaneous voltage. So Vm cosine of omega t plus phi. Okay. So phi is the phase angle. Phase angle is how deviated is our or the deviation of our sinusoidal voltage or sinusoidal signal from its supposed to be, from its supposed angle. Okay, for example, if this is the original signal, and because of certain factors, the signal will be phased, or there will be a change in its angle. It will be shifted. Okay, so that shift is the phase angle or phi. Okay, as you can see here, supposedly at time, okay, or the zero voltage supposedly should be at in here, but because the angle is shifted for some reason, usually this is because of the capacitance and the inductance. Okay, because it is shifted, so we find our 0 degree here, and that shift is the phase angle or phi. Okay, so this is in degrees, this is in radians, since it is multiplied with 2 pi. We cannot, of course, we cannot add the radians from degrees because they are of different angles. So we need to convert one of them to the other. So the angles will be uniform, so that we can perform our arithmetic process. Okay. So usually we convert this one to degrees. Okay, so that we can add them and we can use our arithmetic functions. And this is the conversion from radians to degrees. So 80 over pi. Okay. So again, let's do a recap. This is the instantaneous voltage, meaning the voltage at certain time. This is the maximum voltage. This is the cosine function, which is the behavior of our angle or of our sinusoidal figure, sinusoidal voltage or current. And then omega is 2 pi f, or the frequency times the devolution of our sinusoidal voltage or current. T is time and phi is the phase angle. Okay, so this is the parts, or these are the parts of our what do you call this one again? Our sinusoidal voltage formula. Okay, so I hope that was clear. So I will delete this one. So please take a screenshot if you may. 5, 4, 3, 2, 1. Let's proceed. We have here another formula. This is what we call Vrms. Okay, So RMS means root mean square. Okay, root mean square. What does root mean square means? In the case of our electrical voltage, current, or power, AC electrical voltage or AC electrical current or AC electrical power, root mean square means the effective. Okay, by the way, this is my own words definition. So we have a definition here in the module. I'm just trying to simplify the definition so you can, to help you understand better the subject concerned, which is the root mean square. So this is the effective in the case of our voltage. So the root mean square voltage is the effective voltage, AC, the effective AC voltage that is being used or utilized by our circuit. Okay, in the case of our household power, we have here 220 volts, right? 220 volts, 60 hertz AC. Okay, so we have 220 volts, 60 hertz AC, 60 hertz AC. The question is, this 20 hertz, that is our voltage rating in our household, is this RMS or is this maximum voltage? Okay, so what do you think? So if you're thinking that that is the maximum voltage, you are wrong. Okay, so this is the RMS of our household power, household electrical power. Okay, so 220 volts is the effective voltage that is being utilized by our appliances. Okay, if you will look at our sinusoidal figure, you can see that there is maximum voltage, there is a part that is zero, there is a part that is negative maximum voltage. But of course, our appliances will not to change. For example, if we have an electric fan, so if we will have maximum voltage here, the electric fan will on at maximum voltage every time it reaches zero. Will it turn off? No. Okay, when it reaches a negative voltage, will it reverse the direction of the fan? No. Okay, so the electrical devices will try to utilize a certain value that is effective or the most useful from this sinusoidal voltage, and that is the root mean square. Okay, so the ratio of root mean square and the maximum voltage is square root of 2. So in the case of our 220 volts, okay, so the maximum voltage of our AC household power here in the Philippines is equal to 220 volts. This is RMS times square root of 2. Okay, so if we will multiply this one, this will be equal to, so let's try to solve it together using our calculators. So this will be equal to 311.13 volts. Okay, so our household AC power is actually capable of producing 311.13 maximum voltage. Okay, but again, only the effective voltage there is 220 volts. So that is our root mean square or RMS voltage. Okay, so let's proceed. So we have an example here. So before we solve an example, let's recap what we have discussed so far. Okay. So again, this is the working voltage of our sinusoidal function, or this is the working equation of our sinusoidal voltage. So instantaneous voltage is equals to maximum voltage cosine of omega t plus phi. Omega is equal to 2 pi f. F is the frequency. Frequency is equals to 1 over the period, or 1 over t, capital T. Okay. Phi is the phase angle. So that is the shift of our sinusoidal function, which is affected or caused by some factors of our circuit. Next, we have the conversion from radians to degrees, which is 180 over pi. And lastly, our root mean square voltage, which is equal to maximum voltage divided by square root of 2. All right, so let's proceed. We have an example here. So a sinusoidal current has a maximum amplitude of 20 amperes. The current passes through one complete cycle in 1 millisecond. The magnitude of the current at 0 time is 10 amperes. So what is the frequency of the current in hertz and in radians per second? Letter B, write the expression for it using the cosine function. So express phi in degrees. And letter C, what is the RMS value of the current? Okay. So of course, the formula applies also for the current. So it will be the same. So we have current instantaneous will be equal to current maximum cosine of omega t plus phi. So given maximum amplitude, so Im 20 amperes. That's the current passes through one complete cycle in 1 millisecond. One complete cycle t. Okay. The magnitude of current at 0 time is 10 amperes. So I at 0 time is equals to 10 amperes. So these are the givens of our problem. So letter A, what is the frequency of the current in hertz and in radians per second? So F, so letter A, F is equals to 1 over T. So given period is 1 millisecond. So 1 milli is 1 times 10 raised to negative 3 seconds, which is equal to, okay, so this will be equal to 1 times 10 raised to 3 seconds, hertz, or times 10 raised to 3 is kilo. So 1 kilohertz. Okay. So that's for our letter A. Letter B. Write the expression for it using the cosine function. So express phi in degrees. Is phi given? No. But we are given Im. We can have omega from our frequency. Okay? Phi is not given. How about I? Is I given? Yes, I is given, which is equal to 10 amperes if time t is equal to 0. Okay, so we can try to solve this one. We have I equals to Im cosine of omega t plus phi. Okay. So at time 0, we will solve this using time 0. So we can solve for phi. Okay. I'm out of space. I will solve this here, up here. Letter B. So I is 10 amperes times 0. Maximum current is 20 amperes. Okay, so cosine of omega t. Omega is 2 pi f. So 2 pi f is 1000, but t is 0. Okay, so plus phi. So this will be equal to 0. So we have here 10 over 2. We'll divide this one, 10 over 20. Then is equal to cosine. This will be 0. So cosine phi. We're looking for phi. So this will be equal to the cosine inverse of 10 over 20 is 0.5, right? So this will be equal to 60 degrees. So our phi is 60 degrees. Okay. Therefore, if we will write our equation, I, that will be I, maximum current is 20 amperes. 20 cosine of, again, omega is 2 pi f. 2 pi f is 2 pi times 1000. So this is 2000 pi t. Okay. Phi is 60 degrees amperes. So this will be our I. Okay. Let's proceed to letter C. Letter C is the RMS value. So again, so for our last, we have RMS. So same formula with the voltage RMS. So I RMS, or root mean square, is equals to the max current over square root of 2. Okay. So our max current here is 20 amperes divided by square root of 2. Okay. So this will be equal to, so again, let's try to solve all together using your calculators there. So this is 20 divided by square root of 2, which is equal to 114.14 amperes. So this is our RMS current. Okay, so hopefully the solution was understandable. So we solved for the frequency, the expression, and then the RMS value of the current. Okay, so let's proceed. A sinusoidal voltage is given by the expression V is equals to 300 cosine 120 pi t plus 30 degrees. So letter A, what is the period of the voltage in milliseconds? Letter B, what is the frequency in hertz? Letter C, what is the magnitude of V at 2.778 milliseconds? And letter D, what is the RMS value of V? Okay, so let's solve this one. We are asked for the period. So since this is period, we will go with omega. So omega again is equals to 2 pi f. And f is equals to 1 over t. So letter A. So given omega, so 120. Wait. What? Okay. So f is equal to 1 over t. Omega is 120 pi. So it's equal to 2 pi f. So transposing or transposition of 2 pi will be f is equals to 120 pi over 2 pi, which will be equal to 60 or 60 hertz. Okay? So this is actually the answer to letter B, 60 hertz. So for letter A, our T is equal to, so F 1 over T. So using transposition, T is equals to 1 over F, and F is equals to 60. So T, or the time period now, which is letter A, will be equal to, so 1 over 60 will be equal to, in milliseconds, so 16.67 milliseconds, or 16.67 times 10 raised to negative 3 seconds. Okay. Next, we have letter C. What is the magnitude of V, or the voltage, at 2.778 milliseconds? So let's solve letter C here. Magnitude of V at time 2.778 milliseconds. So the expression for V is equals to V 300 cosine 120 pi t plus 30 degrees. As mentioned earlier, as we mentioned earlier, this is in radians. This is in radians. This is in degrees. So we need to convert this one to degrees. So we can solve the whole equation. Okay. So what will happen now is 120 pi times t, which is 2.778 milli, so times 10 raised to negative 3. So this will be omega in radians. Okay. So omega now will be equal to, so if we will multiply this 120 pi times 2.778 milli, this is equal to 1.047 rad per second. Okay, so radians per second. Again, this should be converted to degrees. So we will multiply this by 180 degrees over pi, which will be equal to omega now is equal to okay, so we will multiply 180 over pi. So this is equal to 60 degrees. Okay. So this is equal to 60 degrees. Now, simplifying our expression, so 300 cosine 60 degrees plus 30 degrees. 300 cosine 90. And we all know that cosine 90 is equal to how much? 0. So 300 times 0 will be equal to 0 volts. So the voltage at 2.778 milliseconds will be equal to 0 volts. And then lastly, letter D, what is the RMS value? So Vrms is equals to Vmax over square root of 2. Vmax again is 300 volts. Square root of 2. Sorry. So Vrms is equal to so 300 divided by square root of 212.13 volts. Up. Okay, so these are our solutions for example number 2. Right. So I'll clear the presentation. So please take a screenshot if you need to. 5, 4, 3, 2. Okay. So I'll clear the presentation. So next. So here we have developed. Here we develop a technique for calculating the steady state response directly. It is important to remember the following characteristic of steady state solution. So number 1, the steady state solution is a sinusoidal function. Number 2, the frequency of the response signal is identical to the frequency of the source signal. Okay, before we get confused by what we're talking about here, this is sinusoidal response. What we've discussed earlier is sinusoidal source, voltage or current. So meaning it's the voltage source or the current source. Sinusoidal response is the output, okay, of the load, whether the load is a resistor, a capacitor, or a inductor in our circuit. So since the source is sinusoidal, chances are the response is also sinusoidal. Same with our DC voltage. Since the DC voltage is the source, the output is also DC. For AC, AC is the source, the output is also AC. Okay? For our passive elements, RL and C. So let's proceed. The frequency of the response signal is identical to the frequency of the source signal. Identical. Term is identical, not the same, but identical. This condition is always true in a linear circuit with or when the circuit parameters R, L, and C are constant. The maximum amplitude of the steady state response in general differs from the maximum amplitude of the source. And number 4, the phase angle of the response signal in general differs from the phase angle of the source. Okay, so that's why we said identical. So meaning when we look at the graph of the response and the source is almost identical, but there will be differences such as the maximum amplitude and the phase angle. Okay. These characteristics are worth remembering because they help you understand the motivation for the Fixor method. So in particular, note that once the decision has been made to find only the steady state response, the task is reduced to finding the maximum amplitude and phase angle of the response signal. So the waveform and frequency of the response is already known. What it's trying to say is that since it is already established, let's go back to our previous slide. It's already established that the response signal is identical to the source signal, so meaning omega t is the same. If it's cosine, if the source is cosine, the response is cosine. If the source is sine, the response is sine. Okay. The only thing that will differ is the maximum amplitude. So if it's voltage, so the maximum voltage is different on the response and the source. Also the phase angle. So the omega is the same, and the sine cosine function is the same for sinusoidal response and sinusoidal source. Okay. That being said, as discussed in the second slide here, that since only the maximum amplitude and the phase angle is different, okay, so what we are going to do in the response is only to find the maximum amplitude and phase angle. So we are having less, or rather the task is less as compared to when dealing with the source, sinusoidal source or source signal, right? And the waveform and the frequency is already known. So the omega of the source will follow to the response. Anyway, since we're only trying to find the maximum amplitude and the phase angle, so we can use another method to help us find these two parameters more efficiently. Okay, so this method that we're talking about is what we call the Fixor. Okay, so what is Fixor? The Fixor is a complex number that carries the amplitude and phase angle information of a sinusoidal function. So the Fixor concept is rooted in Euler's identity, which relates the exponential function to the trigonometric function. So if you still remember our Euler's identity from our advanced math, so that is equal to e raised to j theta, which is equal to cosine theta plus j sine theta. This is the imaginary part. This is the real part. Okay? So what happens in a exponential function or the Euler's identity when we graph it on Fixor diagram? If we will plot it on the Fixor diagram, if we have this is the imaginary part, right? And then this is the real part. Hopefully you still remember your Fixor diagram. Then, let's say we have A. So A is the amplitude. Then theta is the angle from the positive real axis. Okay, so this is our Fixor diagram. So what does a Fixor diagram has to do with our sinusoidal function? So this relationship was already established in advanced mathematics. I don't know if we should still discuss this here, but this is the y part, j sine theta, rather aj sine theta. This is the x part, this is the a cosine theta. So this is a little refresher of our Euler's identity. And this is in frequency domain. Okay, so this is plotted in the frequency domain. Never mind. Yep, frequency domain. And then our sinusoidal function is in time domain. So that is the difference. Okay. So equation 7 here is important because it gives another way of expressing the cosine function and sine functions. So we can think of the cosine function as the real part and the sine function as the imaginary part. Okay, so we have here V, this is Fixor. This notation is Fixor. Okay, so which is equal to this P is meaning the Fixor equivalent of this one. The Fixor equivalent of this one. So this is the Fixor equivalent. Okay, next. I'll clear this one. So this complex number is by definition the Fixor representation or Fixor transform of the given sinusoidal function. The notation P, fancy P, which is meaning Fixor of the Vm cosine omega t plus phi, is read as the Fixor transform. Oh, yeah, I just read this one. Thus, the Fixor transform transfers the sinusoidal function from the time, sorry, yeah, that's what I'm trying to say, complex number domain. Why did I write frequency domain there? Frequency domain is Laplace function. This is Euler's identity. So let's go back here. Fixor transform transfers the sinusoidal function from the time domain to the complex number domain, which is also called the frequency domain. I just contradicted myself. Anyway, throughout this book, we represent a Fixor quantity by using a bold-faced letter. So this one. So equation 8 is the polar form of the Fixor. This is the rectangular form. Again, the difference of polar form, I hope you still remember, that is A, E raised to J theta, polar, A cosine, plus J, A sine theta, rectangular. Okay? So this is the rectangular form. The equation number 8 is the Fixor form. Or the polar form, sorry. Next. One additional comment regarding equation 8 is in order. The frequent occurrence of the exponential e raised to j theta has led to an abbreviation that lends itself to text material. All right, so this one. If you can recall from your advanced mathematics that usually instead of writing e raised to j theta, we write this one. I forgot what this is called, but 1 cis. Okay, this is cis. 1 cis theta. Usually we call it 1 cis theta. In this case, since we are dealing with sinusoidal spans, so this is phi. Also 1 cis phi. Okay, so we use this notation extensively in the material that follows. So of course, since we can transform our sinusoidal function into Fixor form, we can return our Fixor form to the sinusoidal form. So that is inverse Fixor transform. Okay, the problem here is if we are given the function in polar form, okay, like this for example, we can return it to our sinusoidal function. So again, this is B max. This is P. But when we return it to our sinusoidal function, we can only know Vm and phi. We have no way of knowing omega. Okay, so usually we cannot deduce the value of omega from the Fixor, so the Fixor carries only amplitude and phase information. Okay, so when we do inverse Fixor transform, this is usually the answer. we have omega in our answer because we have no way of knowing omega. Again, so this is the notation. So from our Fixor transform earlier, so this is the P when we do Fixor transform to this one. Now, when we do inverse Fixor transform, so this will be the notation. So P raised to -1. Okay. So this is the other Fixor transform is useful in circuit analysis because it reduces the task of finding the maximum amplitude and phase angle of the steady state sinusoidal response to the algebra of complex numbers. So the following observations verify this conclusion. Number one, the transient component vanishes as time elapses. So the steady state component of the solution must also satisfy the differential equation. Number two, in a linear circuit driven by sinusoidal sources, the steady state response is also sinusoidal, and the frequency of the response is the same as the frequency of the source. Number three, we can postulate that the steady state solution is of the form, okay, so this one, where A is the maximum amplitude, B is the phase angle, or beta is the phase angle of the response. When we substitute the postulated steady state solution into the differential equation, the exponential term e raised to j omega t cancels out, leaving the solution for A and B in the domain of complex numbers. So an important warning is in order. The Fixor transform with the inverse Fixor transform allows you to go back and forth between the time domain and the frequency domain. Therefore, when you obtain a solution, either you are in the time domain or the frequency domain. You cannot be in both domains simultaneously. The Fixor transform is useful in circuit analysis because it directly applies to the sum of sinusoidal functions. Circuit analysis involves summing currents and voltages. So the importance of this is obvious. Fixor representation is the sum of the phasors of the individual terms. Before applying Fixor transform to circuit analysis, we illustrate its usefulness in solving a problem regarding adding sinusoidal functions via trigonometric identities. So this shows how the Fixor transforms simplifies this type of problem. So we have an example here to show you why we need to deal with Fixor transform. Okay. So if given y sub 1 is equals to 20 cosine omega t minus 30 degrees and y sub 2 40 cosine omega t plus 60 degrees, express y is equals to y1 plus y2 as a single sinusoidal function. So we are being asked to add two sinusoidal functions. Okay? Remember, we don't, when we solve for using our Fixor solution, we don't care about the value of omega. For example, y1 here to be equal to, if we will convert this to Fixor, so 20, negative 30, right? y2, 40, 60 degrees. Okay? So that's it. That's our Fixor form. We only need the amplitude and then the phase angle. But what's next? We cannot add this to polar forms. So we will convert them into their rectangular forms. Okay? So rectangular form, 20 cosine negative 30 plus j 20 sine negative 30. And then next, we will simplify this one. So we have 20 cosine of negative 30, which will be equal to, let's solve using our calculators put together. So you can practice your calculator techniques. So this is equal to 17.32, while this one is equal to rather minus J10. For y2, okay, so y2 will be equal to 40 cosine 60 plus J40 sine 60 should be equal to 40 cosine 60 is 20 plus, again, let's solve all together using our calculator so you can practice your calculator techniques. 40 sine 60, which is equal to 34.64. Okay, so you have y2, we have y1. Now we can solve for y. So that will be, sorry. So we have y is equals to y1 plus y2. Okay, so y1 here is 17.32 minus J10 plus 20 plus J 34.64. So y here will be equal to, so 17.32 plus 20, we will add the real parts and we will add the imaginary parts as per the solution. So real parts, and then imaginary parts. Okay. So 17.32 plus 20 is 37.32 plus J 24.64. Okay. So this is in rectangular form. Our next step will be to convert this one to polar form. So polar form, again, what do you call this one? That is R theta, right? R is the again, what's the term? Magnitude. Okay, so real squared. Let's just say x squared plus y squared as what we usually use in trigonometry. In this case, 37.32 squared plus 24.64 squared. And no space, but we can do this squared. Okay, square root. So R now will be equal to we have the square root of 37.32 squared plus 24.64 squared, 44.72. Okay, so this is for R. Now for our theta again is equal to the inverse tangent, right? Inverse tangent of y over x. Again, our y is the imaginary part, so that will be 24.64. So inverse tangent 24.64 divided by 37.32. So this will be equal to angle 33.43 degrees. Okay. Now, what happens next? We have our y as in polar form, 44.72, 33.43 degrees. Of course, we need to express this into a sinusoidal function. So in terms of sinusoidal function, okay, so our y now, this will be our Vmax. or it is not stated if this is voltage or current, but this will be the max value. So y now will be equal to 44.72 cosine of, again, omega t will be the same. Then the phasor angle will be positive, or sorry, phase angle. The phase angle will be positive 33.43 degrees. This will be our answer. So that's the importance of phasor, or the concept of phasor, when dealing with our sinusoidal functions. Okay, so that's it. That's for our lecture for this week regarding sinusoidal response.